We talked about the harmonic drive, but to actually drive an actuator, you need a motor. There are multiple types of motors based upon different physical phenomena, and the most common one is electromagnetic. One other type is piezoelectric, used for nano precision motion. Inside electromagnetic, there are further varieties, for example, brushed DC motor, brushless DC motor, stepper motor, AC induction motor, etc. These varieties further have specialized variants. Which variant goes in a harmonic drive depends on the application. In fact, manufacturers sell the motor and the harmonic drive as a pair based on your need. We'll talk about one particular use case today, that is robotics. In cobots, frameless brushless torque motors are mostly preferred because that offers you a compact structure that you can fit directly with the harmonic drive, forming sort of a flat pancake. These motors can be either BLDC or PMSM, short for permanent magnet synchronous motor. Now, a motor consists of two parts, the rotor and the stator. In BLDC, the rotor carries the magnets and the stator carries the winding. It's the reverse in a brushed motor. Now, two technologies are essential here. First, the neodymium magnets, and second, surprisingly, the winding. China dominates in both. There is a misconception about rare earth metals. It's not that China holds all of the global reserves, but the truth is it has invested in the processing and infrastructure for decades, resulting in the control of the economics of the products. Any country can build the same machinery, and people have tried, but China lowers its prices to an extent of making competitors bankrupt. So for India, though it has the ability, India has to go through the cold start problem, where you need enough cushion to cross the inflection point where you have good consistent demand. Not to mention the fierce competition China will give with its cheaper pricing. Defense is a unique sector where the government, for obvious reasons, doesn't want to use Chinese components. So Indian industry is able to cope even at a higher price. We'll talk about rare earth refining and manufacturing in detail in a future video. Today I want to touch upon winding. Because though this technology was pioneered by Germany and Italy, China has caught up and made it cheaper. It's not hand winding or simple machine winding. Also, the wire itself is not the regular cylindrical copper wire we see at homes. It's copper only but rectangular bars. It boils down to packing efficiency. Circles leave out air gaps leading to wastage of space where it could have been more copper to carry the current. So what manufacturers use instead are hairpins. Hairpins are U-shaped pieces of flat rectangular copper wire that go inside the iron stator. The legs of adjacent hairpins are welded together to form a continuous circuit around the circular stator. Let's take a stator with 48 slots with a rotor having 8 magnets. So each magnet will correspond to 6 slots. Now each 6 slot combo is divided into 3 phases. More on this in a minute. Now these slots and magnets are placed such that both the legs of the hairpins don't fall under the same magnetic pole. That's why if one leg of a given hairpin goes in slot 2, the second leg will go to slot 8, following a n+6 convention in this case for all the hairpins. Now to cancel out certain harmonics, which are ripples in the magnetic field that cause vibration and noise, designers deliberately choose the span lower by 1. In our case, that will be a n+5 convention. Additionally, a shorter span means shorter crowns, that is, less copper hanging out the ends doing nothing. And remember, only the straight part inside the iron actually pushes. The crowns are just commuting copper. Shorter commute means less wasted copper, and also it means less resistance, less heat, and a slightly lighter motor. Further, let there be 8 layers in each slot. Now both legs of a given hairpin won't go in the same layer. It'll be like slot 2 layer 1 and slot 7 or 8 depending upon the convention, but layer 2. This is because if both legs of the hairpins start going in the same layers, the crowns of the hairpins in between n and n plus 5 or 6 would all cross at the same height and collide. Shifting layers turns every crossing into an overpass. Moreover, all the hairpins are prearranged and are inserted all at once inside the stator. Then a machine twists the tips of layer 1 legs clockwise and tips of layer 2 legs anti-clockwise, or vice versa. All tips within the same layer move together at once. You can imagine, due to the sheer volume of these hairpins, it is impractically slow to twist each tip one by one. That's another reason why both legs go in different layers. Now let's come to the 3 phases. Imagine a merry-go-round and you are the only one pushing. You push, then your hands leave it. You wait for the bar to come around, push again. The spinning is jerky. Push, wait, push, wait. The worst thing, a single phase from standstill doesn't even tell which way to go. Now bring 2 more friends and stand evenly spaced around the circle. You take turns, you push, then your friend 2 pushes, then your friend 3, then you again, and so on. From the merry-go-round's point of view, someone is always pushing it. The spin becomes perfectly smooth and the direction is unmistakable because the pushes travel around the circle in order. And why exactly 3 friends? 2 could do it, but they cannot be placed at 180 degrees to each other, because we'll end up with the same problem at standstill, which way to go. 90 degrees would do, but at an additional wiring cost. Could you have 10? Sure, even smoother in theory, but now you are paying 10 people for a job 3 do nearly perfectly. Now when you turn on the voltage, the electrons start moving in copper, and that creates a magnetic field, pushing and pulling the motor accordingly to align. And with the help of the 3 phases, the motor is able to rotate a full circle tens of thousands of times every minute, with the controller switching the coils thousands of times every second. The stator, bolted to the ground, acts as the anchor. Fun fact, the stator core isn't a solid single piece, but hundreds of stamped rings to avoid unnecessary heat due to eddy currents. Also, after welding, the wound stator is dipped into a varnish to glue everything in place to deal with vibrations and seal out moisture. That's all the engineering that goes behind every BLDC motor. See you next week.